as we continue to look at polynomials, we want to be really careful that we know this, what we call the leading coefficient test. And so the leading coefficient test is a test that we can perform in order to determine what we call the end behavior of our graphs. And so when we talk about the end behavior of our graphs, we really mean as we have a polynomial function here, as x is getting very large or as x is getting very small. As a matter of fact, as x approaches positive infinity or our x values that we're plugging in approach negative infinity, what are our y values doing? And so the interesting thing with polynomial functions is that on the left and right side, as opposed to the middle where we have this nice little bendy graph and it does kind of whatever, we know that on the left and right side it doesn't really have a choice on what it does. It's either going to fall on the left or rise on the right, or it could rise on the left or fall on the right, or it could have the same behaviors on the left and the right, or it could have opposite behaviors on the left and the right here. And so the way that we're going to determine this is we're going to look at two, I guess, facets of our polynomial function here. And so I'll zoom in up here. But basically, if our polynomial function is written in standard form and our a sub n here, which is our leading coefficient, is not 0, then our leading coefficient is this term up in front here, this coefficient of our x with the highest power. And our highest power is the degree of this polynomial function. Now, the fact is, this test, it gets its name because you look at the leading coefficient. There's something about that leading coefficient that's going to tell us a little bit about the end behavior of this graph. And so what I've done was actually I created over here in Desmos what we call a power function. And a power function is a polynomial function that basically just has one term, and it's that term to some power here. And so when you look at my power function here, what I want you to notice is right now my a value, since this is the only term, is technically the leading coefficient. Right now I've got my a equal to 1. And likewise, we say n here, well, that would be my highest exponent, so that's the degree, and right now my degree is 1. And so what I want to do is I want to be able to take a look at a graph, first of all, like this linear graph that is really just 1x, y equals 1x. So this graph that hits at 0, 0 and goes up 1 over 1, up 1 over 1 forever and ever here. And actually, I'm going to zoom out a little bit here. That's a little bit, there we go, that's better on the eyes. So anyways, we're taking a look at this graph here, but basically I could see that this graph definitely falls on the left and rises on the right. And so to state that scheme, I suppose we could draw a little diagram here. We would say that this graph falls on the left and rises on the right. And so just to determine this end behavior would be such a powerful thing to know about our polynomial function before we even graph it. So how are we going to be able to determine this? Well, here's what I want you to pay attention to. Right now, I'm falling on the left, rising on the right. Let's mess with our degree and see what kind of patterns we can get to happen. So if we have a second degree thing, that's y equals 1x squared. Of course, we get our parent quadratic function here, but we rise on the left and right. If we go third degree, we get 1x cubed is our function. This is our cubic function that goes through 0, 0, 1, 1, but is also this odd function that goes through -1, -1, positive 2, positive 8, -2, -8. And so this function right here, you can see falls on the left, rises on the right, on a smooth curve. Let's go fourth degree. Now, fourth degree, I hope you notice this. Fourth degree kind of looks like second degree, but it's a little bit flatter in here between -1 and 1. Can you see it? Can you see it? Right there. That's a little smoother, a smooth curve. And it's a little bit steeper on the outside of -1 to 1. And so what I want you to recognize is that x squared and x to the fourth really are kind of like the same graph, except for x to the fourth is going to grow a little bit faster when we start plugging in numbers bigger than 1 or smaller than -1, and it's going to shrink a lot faster because you're taking smaller numbers to the fourth power here in between -1 and 1. But basically, again, it's end behavior I want to look at here. So rises left and right. Fifth degree, falls left, rises right. Sixth degree, rises both sides. Seventh degree, okay, falls left, rises right. What I'm seeing is that every time my degree is even, the left and right side have the same behavior. And every time my degree is odd, 3, 5, 7, my graph has opposite behaviors on left and right side. So one key fact that we're going to look at here is that the degree, if it is odd, okay, we have opposite behaviors on the left and the right. If our n, our degree on our function here is even, we have the same behaviors on left and right. So where does this leading coefficient come into it? Well, I want you to notice something, that one side of this graph was always rising. I hope you notice that it's the right side here. And the fact is that right side was rising because our leading coefficient here is, well, just to tell you, it's positive. So if I were to make my leading coefficient a negative here, I'll go -1 just to be nice. It doesn't have to be any particular number, but negative, you'll see that every time, no matter what my degree is now, I'm falling on the right. So the fascinating thing about that leading coefficient is it always tells you the right-hand behavior of any polynomial function no matter what, if you know its sign. And so that's of course the other thing that we had listed here in our notes. If a sub n, which is our leading coefficient, is positive, hey guys, we rise right. If a sub n is negative, we fall right. Okay, if a sub n is positive, we rise right, and if a sub n is negative, we fall right. And so what I want to be able to do is to 100% of the time look at a polynomial's leading coefficient and degree and be able to determine the end behavior. So that's exactly what I want to do here in 15 through 18. I want to use this leading coefficient test to determine the end behavior of our graph of this given polynomial function, and then we're going to match these with the graphs here labeled A through D. So what I want to do basically is I'm going to put a set of parentheses on each of these. I used to put a comma, but then people thought it was some ordered pair. So I don't want to do that here, but what I want to do is I want to go through and determine the left and right hand behavior and either use a down arrow or an up arrow to indicate rising or falling. Okay. So looking at number 15 here, I'll just point this out first. Remember that your leading coefficient, which if this is in standard form is this first coefficient here, if it's positive or negative, that tells us about which side of our graph. Okay. Remember that it tells us about the right side of our graph. So that being said, I can tell you right now that the right side of my graph has to fall. Now, if I ask you about the left side, look at your degree here. Because we have an even degree, what do we know about the end behavior of the left compared to the right when we have even degree? Well, it would have to be the same. So just because I know my negative leading coefficient is negative, I know the right side behavior. And then because I know my degree is even, I know that the left side would have to match the right side. So for all of these here, what I would encourage you to do is go through and determine the right side behavior. As a matter of fact, we could do that right now. We say this here, a positive leading coefficient rises on the right. This down here, now this is interesting, x minus 3 times x minus 3 is what this really truly means here. I'm actually going to FOIL this out and I want you to see something here. I get x squared minus 3x plus 9, which ends up becoming x squared minus 6x plus 9. Now this right here has a positive leading coefficient, but I could have told you that up here just because of this guy right here. So this leading coefficient out in front is more indicative of what this will do here. And so I know that this rises on the right because our leading coefficient is positive. And over here our leading coefficient is negative, so we fall on the right. Now the hard part about this, oh I'm sorry, I say hard part, I mean easy part about this is once you get the right side behavior, we'll just go look at the degree to say, would it be the same or different as the right side behavior on the left? So because I have an odd degree, well, what do you know about odd degree? Odd degree is differently behaving on the left and right. So if that was up, this is going to fall on the left side. For this graph here, we say, what's our degree? Now, I did FOIL this out and we get a second degree, but what I want you to notice is we took a first degree times itself. So we get a first degree times a first degree. We get a second degree polynomial function. So we get an even degree. You guys, even means that this left side would have to be the same. And then over here, because we have an odd degree, what do you think our left side should be? Well, our right side was down. This is an odd degree, so this must rise on the left. So now that we've kind of assessed the situation here, we say, okay, well now I know what the end behaviors of our graphs are. And it's kind of nice that these examples use one of each. I want to match these to our graphs. And so when I look at this down here, I say, well, which of these could possibly match with number 15? There's only one that could, and that would be letter B. And letter B because it falls on both sides. Okay, we have this fourth degree thing. Number 16, we had falling on the left, rising on the right. Well, this could only be one option here. This is letter C. This third degree thing kind of looks like a cubic graph, kind of, except for we get a little bit more bendy graphs sometimes with polynomials, but we say it would rise on the right, fall on the left. Now, number 17 would rise on both sides, and the interesting thing is we actually get a second degree thing, which is a parabola. So two ways that we could identify this. It's the only quadratic function here, and, okay, excuse me, we rise on the right and rise on the left. So this would be A here. And then number 16, sorry, we should have written C up here. So that leaves D for down here, but we see rising on the left, falling on the right, and that's definitely clearly the pattern that is exhibited with the graph on letter D. So know how to use your leading coefficient test by just determining the right hand behavior first, and then matching the left hand behavior if it's the same or different. Cheers.